Good morning and welcome to our lecture on TP 4165, computational heat and fluid flow. So last time we started looking at the linear advection equation and we ended up with the form of the equation in integral form that we can write where we introduce the cell average. So, and what we ended up with was the formula that is the essentially the finite volume approximation to the finite volume method for the 1D linear advection equation. And if we do that with the index notation, where we assume that we have our domain, say from xa to xb, we have divided that in, and we have here, say, we assume we have the temperature, that is what we are going to advect in our example, with the velocity u, and we assume then that we have our cells. They don't need to be equidistant. That is the strength, as I told, of the finite volume method. And we consider then the control volume J, so that would be the cell J. That would be the midpoint xj, and we denote the faces by xj minus 1/2, that is the left face, and by xj plus 1/2, that is the right face. So then, and the length of the cell or this control volume, which is just an interval in our case, is delta xi. So, and the form that we can use then, that we can write the finite volume method then, is this length of the control volume times the time derivative of the finite volume approximation of the cell average. Remember, what we are doing here, we are computing cell averages. That is a mean value of the cell. But we locate these values at the midpoints. We can show that analytically that that is correct to second order. So if we have here the cell j plus 1, then we might have a value there. So that would be the tj plus 1, and we might also have a value on the left, tj minus 1, that is located then at the midpoint of the cell j minus 1. So we have then here an equation where the time derivative of the cell average approximation in cell j is involved. And then we have the fluxes, and they are now the convective fluxes, and we have a flux over the right edge, that is the eastern edge, that is then at j plus 1/2, and you have a flux over the left face j minus 1/2. So that is the convective flux balance, you could say, and that is 0. And we mentioned already at the end of last lecture that it depends now in the way we approximate these fluxes, these convective fluxes, which finite volume method we get in the end. So we start now to look at some of these possibilities. The first possibility we have already seen mentioned last time, that is the central finite volume method. In the central finite volume method, we approximate this flux at the phase j plus 1/2, that is the flux that we have here. So at this phase, we concentrate on that. We approximate that by the mean of the flux, of the convective flux, and that is the following. We say we have the equation 7, that is the convective flux at the phase j plus 1/2 is then defined by the average, the arithmetic average of the value of ut at in the cell j plus the value in the cell j plus 1. So we take simply the arithmetic average. And that is motivated just when we draw a line, if we connect the values at the cell j and j plus 1, and then that would give us the mean. And remember, the u in our case is just constant. So that gives us then, it's somehow intuitive, but it turns out it has some properties that do not make it very suitable. First, before we get to that, just a remark on the flux at j minus 1/2. We usually concentrate on that because to get the flux at j minus 1/2, we simply shift the index by 1 to the left. So when we want to have j minus 1/2, we simply have here then j minus 1. J minus 1 plus 1/2 is j minus 1/2. So that becomes then j minus 1, and that becomes j. So we could also write it very simply that we say if we have here a minus, then this will induce a minus here. But it is enough just to mention how things work for just one edge. J plus 1/2 is usually then defined. Okay, so also when you do the programming, by the way, disadvantages, not in that case it doesn't make much difference, but to compute the fluxes, use the fluxes. Because when you compute the fluxes, you compute them once. If you compute them for each of these flux balances, for each cell, you compute them twice. You compute them each time for the flux for the eastern and the western. But when you compute them once, you can reuse the flux that you have here been using as the eastern flux. You can use that for the cell j plus 1 as the western flux. It's the same. So you can save computing time when you compute the fluxes only once. You have, of course, to invest an array for that, but if you have larger problems, then it makes sense. For this, it's not much of a difference. Now to the properties of the method. If we look at that and we do an analysis, a consistency analysis, we will find out that this method is second order. This flux approximation using this central approximation is second order. So we can state that this method, this flux approximation, is second order accurate on an equidistant grid. When we have equal grid size, and that means that the truncation error, that means ES, that the truncation error then is of the order delta x squared. So that is a good thing. But if we use now this approximation here for the convective fluxes in here and also here, and we approximate this, and then it becomes an ODE, right? We have an ODE then. If we approximate that by the explicit Euler method, you might know that the method that we get is unconditionally unstable. So it's essentially useless. So we can state that the explicit Euler method that is for the time discretization, for the equation for the finite volume approximation that we have here, 6 or 6b, with the central finite volume method is unstable. And you will experience already instability for exercise 2, not for the linear advection equation, we take that in exercise 3, but for the heat equation. There you have also a stability condition, you have a stability condition. There it is conditionally stable. For the von Neumann number within a certain range, the method is stable. So and you're asked also to test what happens when you violate this condition. And then you see what is happening. You get very simply, very quickly, enormous numbers, 10 to the 70 or something, which are simply garbage. So, but this method, you can try anything. It doesn't work. It is really useless with the explicit Euler method. But, and we can show that it is unstable by the von Neumann stability analysis. However, if we replace the explicit Euler method by a suitable Runge-Kutta method, then the method is stable. So that you can also remark. But Runge-Kutta methods and the favorite is then the classical fourth order Runge-Kutta method that I call it RK4. That is the one that you usually learn. That is the classical explicit fourth order method. And also implicit methods, for example, implicit Euler method or PDF or whatever, suits all different Nicholson. So implicit methods, they are stable. So you can use them. And when you have problems for waves, for example, when you have a smooth solution, then this approach using, say, Runge-Kutta method is really useful. However, if you have discontinuous problem, shocks or any discontinuity for the temperature profile, then you will have a lot of problems also with these methods. So, if we want to qualify this central finite volume method, then we can say, compared to the method that we are going to see next, that is an advantage. There's a plus here. So the advantage of the method is that it is second order. So that is a good thing. And the other positive feature is that it does not have numerical dissipation. We shall see that for the next method, which has numerical dissipation. So that means when we use this method, the central finite volume method, to propagate waves, then the waves will not decrease in amplitude. It will, if they are clear sinus waves. We can have an error there, we'll come to that later, that is called dispersion, so that the wave is propagating too slowly compared to the exact velocity u. But the amplitudes are not dissipated, so you can really follow waves over long distances in space and over long times. However, when you do that, you really need even higher than second order. You need fourth, sixth, eighth, or you need even higher order methods. But that's another story. Of course, the big disadvantage is that the method is unstable with the explicit Euler method. That is a big disadvantage for the explicit Euler method. And as I already mentioned, you have also the problem with oscillations when, or you have problems with discontinuities. That manifests itself with oscillations at the discontinuities. Also a disadvantage. We have oscillations. If we use one of the stable methods, we have oscillations near discontinuities. So that is the qualification. So essentially, for our purposes, if we want to compute discontinuous flow, this method is not suitable, even with the stable methods. So instead, we look at another method that we shall also test later on in exercise 3, and that is called the Upwind finite volume method. So that is similar as we have seen for the finite difference method, but here we can give now also other arguments for it. Then the flux at the phase j plus 1/2 is approximated in the following way. Now we let the velocity decide which flux, convective flux we take. So we put the finger in the air and look from which side the flow is coming. When it's coming from the left, then the left ut is propagated. So in that case, we take the ut at j. And that is if the velocity is positive. Because then the flux is propagated from the left, and then at the face we take that value. If the flow is coming from the right, then we take the value then that is coming from the right, which is j plus 1, tj plus 1. So that is then, we have to make a choice here. And if u is 0, then the whole thing is 0, then we have no convective flux. So how can we motivate this choice? Well, the way that I just took is one way to say, well, from which side the wind is blowing is transporting the temperature. Another way to look at it is to consider what is happening at the face if we consider the exact linear advection equation. So if we consider that equation there at the face. And that we can imagine the following way. We think we are here at the phase j plus 1/2. We have x, we have t, and we assume we are here at the time level, at the old time level, tn say. Here we have the phase xj plus 1/2. Here we have the cell j, and here we have the cell j plus 1. So then we have argued we are at the midpoint, we have xj, here we have xj plus 1, and we have some values. For example, midpoint is here, and there we have then our cell average located. So that is then the tj, say that would be then at the time level n, if we take it at that time level. And then we would also have a cell average, say here. That would be then the tj plus 1. That is our approximation to the cell average in the cell j plus 1. And now we make an assumption. We assume now that the distribution in the cell is equal to this value, so that we have this distribution here. So that in the whole cell we assume this is our initial condition for what we want to solve. Likewise in the cell, in the next cell. Here we might have another value, here we might have another value. We don't care about that at the moment. And then we simply solve that exactly. This problem to get the value at the new time step. So what will happen? We imagine, we assume now, that is an assumption that we have to make. We have to decide on the sign of u. We assume here for this discussion, for this point, that u is positive. So then the temperature profile will move to the right? Because we have then a propagation of the whole velocity profile to the right. So after a certain time t, so let us assume then the profile will have moved in, and it will be like that. So we'll then have, this will be here, this will be here, and our profile that has moved in, this distance here, that we can quantify. So the first one is the yellow one. The yellow is the solution at t, that is the exact solution, at of x and at the new time level, tn plus 1, with this initial condition. And this distance here, that is the distance that the the temperature profile has traveled in the time delta t. And that is u times delta t. That is the distance the profile has traveled in the time step delta t. Because here we started with a time tn, so the n indicates time tn, and here we have traveled to tn plus 1. The difference in time is delta t. So then we see what is happening at the phase. At the phase, we see that we have the value from the left, the tj. So that is the value that we have at the phase, because that is the problem that we have. We want to know what is the flux at the phase, and it is then determined by tj. So then we will have this solution, utj. But you also see, if we take the time step too large, that is, if we take this traveling too large so that we get here, then what we have here in tj will have traveled across the phase. And we will have then, for example, the value that we have here at tj minus 1. That we don't want. So we want then to restrict that by saying that the u delta t has then to be smaller or equal delta x. If it's equal, then we just happen to be at this point again, but we can allow for that. But we have to restrict the time step. We shall see that later on. But the point is that by this argument, we see that the value determined for the flux is determined by the value of t in the upstream cell, which is tj. If we have the opposite, that we have the u is negative, so then we will have a situation that is x, we have tn, and if we have u negative, so that is now a new situation. So we have here the tjn, and we have here still our boundary, tj plus 1/2, our cell. We have our cells here, and we have here our tj plus 1. So we assume again similar initial condition. And in this situation, the whole thing will travel to the left. And then, after a while, this will have moved in. And let's see, we'll have something like that. That will move in, something like that. So, and then, again, this distance that has traveled, so this distance here, let's see, this distance here, that is again u delta t. Now it is negative because u is negative. And now the temperature at the phase is determined by the temperature upstream, which is now tj plus 1. So therefore the flux, the convective flux, if u is negative, is u tj plus 1. So that is a way to view the approximation that we do with the Upwind method. And this technique, by assuming that the cell averages determine an initial condition to the linear advection equation that we then solve exactly, is the idea that was invented by Godunov for nonlinear problems. And we shall come back to that when we consider nonlinear conservation laws, because there it shows its full strength. But here is already good to understand the idea here for the linear advection equation. So then we have this method, and then we can do the discretization in time. And now we can in fact use the explicit Euler method. So that is now possible to do, and we shall do that. Let's see. The yellow here was again, just let me add that for completeness. The yellow solution here was the solution with this initial piecewise constant initial condition at the new time level n+1. Okay, so now we look for the discretization in time. So there we have use the explicit Euler method. For the Upwind finite volume method. And then we can get that in the following form. Take it first in a general way. Remember the equation 6b that we had seen just in the beginning today from last time. That was the length of the interval, and now we do the discretization of the time derivative by the explicit Euler method. That means for the cell J, we take the difference of our approximations at the new and minus the old time level and divide by the time step size, delta t. And then we assume now that u is positive, so that is important. Assume u is positive, then we can use this approximation here for the flux at j plus 1/2, and for j minus 1/2 we do what we saw before. We simply take the index 1 to the left, that one lower, that is, we have then j minus 1 here, j minus 1, and j. So the interesting thing for us is then this one. So then the flux at the phase j minus 1/2 is tj minus 1. That is then the upstream value to the phase j minus 1/2. And that is equal to 0. And important now is that these are at the old time level. That is then the explicit Euler method. And here we are general. We can have any grid size, but as I told you, the grid size should vary smoothly. And now we make an assumption. We make the assumption that the grid size is equal, so that we have an equidistant grid. So if we have an equidistant grid, that is delta xj is equal to delta x constant, then we can express this equivalently in the following form, that is 9b, then this becomes simply delta x. And then we can divide by the delta x and multiply by the delta t. So again, we multiply by delta t over delta x to get rid of those here. And then we get here delta t over delta x times u. We can factorize u, and then we have this difference. We take that to the right-hand side, and then we get the following. We get then that the solution in cell J at the new time level is equal to the solution at the old time level minus, because we brought that on the right-hand side, then we have factorized the u, we have multiplied by delta t divided by delta x, and then we have here this difference, tjn minus tj minus 1. So now we have written it in the form that we could easily use for programming to get the value at the new time level in each cell. And there we see an important parameter which will accompany us further on, and that is this parameter. We have already some understanding of its meaning. It is the ratio of the distance that the temperature profile has traveled in the time delta t. That is u delta t. Here it was negative, but we are discussing now the positive, so that is positive in our case, with respect to the grid spacing delta x. And this ratio is called the Courant number. That is after, or Courant Friedrichs-Levy number, that is after the people who first used that actually in a proof in 1926. So the quantity that we have here is then defined as follows. That is the quantity Courant, that is after Richard Courant, who later founded the Courant Institute in New York. He had to flee from Nazi Germany. That is, or CFL, which stands for Courant Friedrichs-Levy. Number. So that is the name, and it is then the following. I use this notation capital C. I think it's also used in our textbook, and that is in our case then the ratio of the distance traveled by the temperature profile or whatever quantity is transported in the time delta t divided by the grid spacing delta x. And if u is negative, then the Courant number is negative. But in our case, now u is positive. So now we have this, so then you see here, then we can just write a C here. So we need to compute that in the beginning, the Courant number. And then we have here just Tj, which is actually 1 minus C. Of course, the Tj is appearing here, then plus Courant number times the Tj minus 1. So now we want to understand from where does the stability limit come that we might know or not know that we have for this method. There is a stability limit. We can argue by it in the following way. We can look at the xt diagram where we then go back again to the finite difference thinking. We could also imagine that we are here at the midpoint where we have the xj, and we have here the midpoint xj minus 1 if we think of the finite volume method. If we think of the finite difference method, these are just our nodes. So we imagine that we have, so that this is the time level Tn. So this time level is the Tn, and the time level that we want to compute, that is the time level, so this time level is the time level Tn plus 1. So that means we have to do 1 times the delta t to get from this time to this time. So that means this distance here is delta t. So the question is now, what is the solution at xj at the new time level? We know that from the exact solution. We have argued we can solve this linear advection equation by using the characteristics. We simply look where is the characteristic curve going, and then we might get the following. We might get like this. So in that case, we assume then that the x of t dt is equal to u, which we assume here to be positive. So then we have a positive slope. So that is then the characteristic. And then we know that the solution here is determined by the foot point of the characteristic, by this point. That determines then the solution, because the solution is constant on characteristics. So then we are here. And what is this point? We know it because this distance here, that is the u delta t. So this distance here, this distance here from this point, let's see, I can get that a little larger. So this distance here from this foot point to xj, this distance is u delta t. That is the distance that the temperature profile has traveled in the time delta t. Because this distance is, as we argued before, this distance is delta t. And dx over delta t, that is then this distance, u delta t divided by delta t is u. That is a slope. So then we know this value. So we know then that this value here is then xj minus u delta t. And that is the point where we have to take the solution at the old time level. If we take that, we know it is constant along characteristics, and then we have the solution where we need it at xj at the new time level. So now to get this an approximation to this, because we usually only know the values at the nodes, or in our case, we only know the cell averages in the finite volume method, we have to do some interpolation. And to be able to do an interpolation, this point must be between these 2 points. If this is outside, if we choose delta t too large, then we will get outside. Then the values that we have here and here at the old time level do not tell us what is happening outside. So we have to require that this point is inside the interval that we use for determining the solution. And we can express that mathematically to say that the exact domain of dependence, which is this point, has to be inside the numerical domain of dependence, which is this interval. Then we can do an interpolation, otherwise not. So we note that. So we require that the exact domain of dependence that is of the solution at the new time level at xj, and that is then the point xj minus u delta t. That is our, you can say there's just one point. That must be contained in the numerical domain of dependence. And that is in our case the interval xj minus 1, xj. And that means then that this point has to be in this interval. So that means we test that the point xj minus 1 has to be smaller or equal this, that is then the xj minus u delta t, and that has to be smaller or equal than xj. And if we look at that, then we can argue that if u is positive, or if the current number is positive, then this is okay. So that is okay for, we take it to the current number, greater or equal than 0, because the current number then tells us about u. And this guy here, that is xj minus 1 plus delta x. So you see then the delta x we get then, if we, so that is equal to this, equal xj. If we have then this inequality, we see we can then cancel the xj minus 1, get this on the left hand side, divide by delta x, and then we see that this inequality is okay for current number smaller or equal than 1. Some of you might recognize that from the previous course, TP 4180, that was actually an exam question. So then the condition that we get here for stability, and that is what we then, what this comes down to, this is another way of arguing for stability, that we get from this the requirement that the Upwind finite volume method, that is the explicit Euler method, for the Upwind finite volume method with u positive is, according to this argument, we shall have also other arguments, is stable for, and that is the condition that we get. We have it here, 0 smaller equal to current number, smaller equal than 1. So that is then the stability condition. If we would use the Upwind method with u negative, then we would get that C has to be smaller than 0, because C is u delta t over delta x, but larger, greater equal than minus 1. So in the end, we can argue that the explicit Euler method for Upwind finite volume method, and that was the one that we discussed, that was in the beginning, it was the number 8. So there we have it for both positive and negative u. Is stable for, and the general condition then is, then I call it number 11, that the absolute value of the current number is smaller or equal than 1. And that is also called the CFL condition. Again, after these three people who use it for the first time, Kuran, Friedrichs, and Levi. Okay, so what else can we say about this method? It is first order accurate in time, because we are using explicit Euler method, and we are only using either Tj and Tj minus 1 or Tj plus 1 and Tj. It is only first order in space. So that is the good thing, that but it's a good thing it's stable. So compared to the central method, it is less accurate, because the sample finite volume method, that was second order accurate in space, this is only first order accurate. So the truncation error, and also the accuracy of the method, is order delta t and delta x. That is of the explicit Euler method for the Upwind method. That is first order accurate in space and time. The advantage of the method is that it is robust, Robust means that it can handle large discontinuities so we have large, in our case, temperature discontinuities that are transported. That can be used for that without need to change the scheme. So that means that is called robust, so that you can use it in many also very challenging situations. However, the disadvantage is that it is quite dissipative. And that means that discontinuities are smeared. They don't stay sharp, but they get very, very smooth as we proceed in time. And if we have waves, then the amplitudes finally die out, so they decrease. Even though that they should stay constant, that they are decreased. It is like as you have added viscosity to it. And it is, as we shall see, also what we in fact do by this method. There is one important exception to all this, and the exception is where the method actually is accurate, even accurate, when in a particular situation, when the current number is 1 for u positive, or minus 1 when u is negative. So note that is the exact, so that this method that we discuss, explicit Euler method for the Upwind finite volume method, is exact, which is a very nice feature, for the current number equal to 1. We can also show that. Okay, so I think we stop here for the break. But maybe before you go to the break, you think already about the following. I'll ask you then after the break more. It is common to have a reference group for each course, which gives feedback to me and also to Jürgen, the scientific assistant. So it would be nice to have people in the reference group. So after the break, I'll ask you if you're ready to join the reference group. Okay, so now 15 minutes break.